yesterday, last year, that I was supposed to give the LSM seminar, and of course everything was shut down around that time. So it's nice to be back and to have them up and running again. And so today I chose a topic that's a little bit a departure from what I usually talk about, where I would say my research group is mostly focused on photonics and optical interactions with nanomaterials and organic semiconductors. But many of our applications are in devices, optoelectronic devices. So to really integrate photonic structures well with optoelectronic devices, we have to think about electronic behavior as well, of course. And so that's something that's always sort of at the back of our mind. And, we've had projects over the years trying to find ways to better integrate photonic structures, especially plasmonic structures, into polymer-based organic optoelectronic devices. And so I'm going to talk today about a few case studies. Some are more recent, and then a few older studies that are on this topic of how to improve interactions between metals and conducting polymers or conjugated polymers used for optoelectronic devices. Oh, let me see. How do I go forward? Okay, Zoom isn't one of my favorite ones. Okay, so the three topics I'm going to talk about today they're just three different types of interfacial layers that we've been studying on silver electrodes. We choose silver because silver is a very good plasmonic material, and it's really the best if you're going to try to improve light management in a thin film photovoltaic device or a light emitting diode. Then you would want to use silver because it has the best lowest loss plasmonic properties. It's also highly reflective and is a very good conductor, so also makes a great electrode. And we're going to talk about some interfacial layers that we've applied to silver. One type would be metal oxides, native metal oxides, in order to get better charge injection into conjugated polymers, in this case, a fluorine-based copolymer, F8BT. And this is work by one of my PhD students, Zhangkai Cheng, that we published a few years ago. I'm also going to talk about collaborative work that we did. My graduate student Sneha Srikumar has been conducting with Marzea Hedrari from Rutgers Newark, who works with Elena Gallipini. So we've been collaborating on introducing self-assembled monolayers onto silver to improve charge injection from silver into F8BT. And also I'll talk about older work that we've done in my group on looking at, rather these really we're classifying as P-type interfacial layers, also looking at N-type interfacial layers, where we've used 2D materials, MOS2, to improve charge collection from a photovoltaic layer into a plasmonic electrode. And so the challenge we've set ourselves is to demonstrate efficient charge transport across a polymer metal interface in devices fabricated using the inverted approach. And this is important because this is not commonly done. So normally in optoelectronic devices, you build them on an ITO on glass electrode. So, and then you start with ITO on glass, that's the transparent electrode. You put usually a hole or electron transport layer, then this organic semiconductor, and then the metal top contact with another interfacial layer in between. So building it directly on the metal really isn't done at all in organic optoelectronics, but you do see it a little bit in the organic field effect transistor community, and I'll mention a little bit about that. We want to build them in this inverted way. So building our device on top of the metal electrode, because it frees us up to use all sorts of different shapes and ways of fabricating the metal electrode, which helps us create better light management structures. If you do it as is conventionally done, where you're depositing the metal as the last step on top of the organic semiconductor, then you can't really control the metal surface geometry or structure. You have to do some imprinting into the polymer, and that creates all sorts of variations in the surface of the silver. So we want to be able to integrate silver nanostructured electrodes to improve light management in optoelectronic devices. The first study will be on these native metal oxides, but I want to give some background on why we're doing that. This is sort of the general scheme of that motivates us. Inverted fabrication of these devices would be better for light management electrodes. Typical geometries for optoelectronic devices have the transparent electrode and a planar cathode. So the metal is the cathode. It's the electron injection layer or electron collection layer. If you switch it and make it an anode, so that the metal collects or injects holes, then you can create improved lifetime. So this has been shown by a number of research groups. You can improve the stability of the device. And then in theory, if you add plasmonic structures to the metal, you can improve the efficiency as well. So if our goal then is this inverted structure where the metal serves as the anode for hole injection or collection, as that's how we define it in organic optoelectronic community, and then with metal structures on it, then ideally to improve efficiency and lifetime. And our initial idea was to help with charge injection or collection by partially oxidizing the metal, in this case the silver, because you'll form p-type semiconductor hole injection layers or hole collection layers. So our first study was on the formation of native metal oxides and how they can be used to affect the injection or collection of electrons from an organic semiconductor layer, as well as improving the stability. And of course, the reason you'd want to try and improve the stability too and use silver as an anode instead of a cathode is because as silver over time will actually, even inside in a device, will form oxides or compounds on its surface that will typically increase the work function or make it more negative on the energy scale. So in other words, it'll be better for matching with the highest occupied molecular orbital of the semiconductor rather than for electron injection into the LUMO, lowest unoccupied molecular orbital. So you can also see some examples of inverted and conventional device stability that have been published in the literature with silver. You can see in the inverted situation, the devices are much more stable because as silver degrades over time, it'll still become a better anode. It'll become a very bad cathode. And so the advantages of using high work function metal electrodes like gold or silver, for example, in inverted devices is that you create better stability and you also eliminate corrosive P.PSS layer, which also is a cause of instability in organic optoelectronic devices. It also potentially enables ambient fabrication and storage and, as I mentioned, improves device stability. The problem is the efficiency is not as good typically in the inverted devices compared to the conventional because of control of this interface, as well as just the lack of studies that have been done to develop these inverted structures or devices. Just before I get into our own work, I want to just talk as well about charge injection at the interface. In polymer materials, usually non-interacting interfaces are formed when we spin coat the polymers on metals. And so we create what would be called a Schottky-Mott junction. So when we think about how the open circuit voltage, for example, of an organic solar cell changes with the work function of the electrode or some difference between the LUMO that's affected by the work function of the electrode, you have a very significant change in the open circuit voltage with that. So that's very sensitive to the change in the work function of the metal. So that's for the polymers spin coated on metals. However, interestingly, when you thermally, that's for polymers spin coated onto metals. Interestingly, if you thermally evaporate the metal onto a polymer, you'll create Fermi level pinning. And so you'll see a very weak dependence of the voltage on the work function of the metal. And so my point is that when we create devices using the inverted fabrication method, we will have a very high sensitivity to the work function of the electrode. Whereas in the conventional devices, when the metal is evaporated, you have very little sensitivity to the work function of the metal. So it becomes very important in these, when you're doing inverted fabrication then, to be able to control the work function of the metal electrode. And so originally in one of our early studies, theoretical studies, we set out to calculate how can we create, or what would be the most suitable interfacial layers to use on a metal anode in an inverted optoelectronic device. In this case, it was a solar cell, P3HT, PCBM based, so very conventional organic polymer based solar cell. And we looked at a range of potential metals as well as metal oxides and other interfacial layers that we could use to see which one would work best for optimizing the device performance. And these are just energy level schematics showing the range of the energy levels or work functions of the different materials that we studied. So this was early work by one of my graduate students, Chris Petukov, that we published back in 2014, but I'm using it as an introduction to as a motivation for why we're studying certain oxides. And what you can see here is in the inverted devices, if you look, for example, at silver oxide, here it matches very well with the this is Ag2O, it matches very well with the HOMO level of P3HT. So it's very good potentially as for charge collection, and will reduce any barriers to charge collection, hole collection in particular. And then we did some calculations of open circuit voltage as a function of work function for all of the various materials that we were interested in using. And you can see that for a conventional device, as you increase the work function, then the open circuit voltage drops significantly once you start using a high work function metal as the cathode in this case. And that makes sense because you're basically you're going to create a large barrier for electron collection. For the inverted devices, the opposite case is true. You create a much higher open circuit voltage when you use a P-type interfacial layer between the polymer and the metal. Or the opposite side was a conventional zinc oxide used for the inverted device and MO3 used for the conventional device. And we also factored in these potential interface dipoles, the case where we would have a very strong dependence on the work function and also a weaker dependence. You can see even then you do get the same trend holds, but it's a much weaker trend when you factor in the weaker interface dipoles. So we also looked at the effect of parasitic absorption in these electrodes on the performance of the device, the short circuit current density. You can see as well that many of the metals are actually absorbing a lot of the light, so we call them lossy metals. But if you look at, for example, silver oxide on silver and silver in general, it has the lowest parasitic absorption. So again, it's, as I mentioned earlier, it's the best optical metal as well as being the best electrical conductor. And those go hand in hand. The best plasmonic structure response will be created from the highest conductivity metal. And so from this study, we thought that using silver oxide on silver might be a good way to help us stabilize a silver electrode and improve its work function so that we could get a good open circuit voltage as well as good short circuit current density. And here again, this is actually where we did the calculation of the power conversion efficiency, again showing that low work function metals are ideal for the conventional configuration, but they're unstable. So they create high efficiencies in conventional devices. And then high work function metals, which are typically air stable, are ideal for high efficiency inverted BH2 photovoltaic devices. Metals capable of supporting surface plasmons can therefore result in high efficiency inverted devices, and oxide formation can be favorable as well for the device performance in the case of silver oxide, for example, or copper oxide. They will actually aid in improving or maintaining the efficiency. So that motivated us then to look at silver oxides on silver as a way to improve and stabilize the performance of the inverted devices. So one of my PhD students, John-Kai Cheng, in a recent study, looked at the performance of silver oxides on silver made by oxygen plasma, low power oxygen plasma exposure of silver on the performance of F8BT hole only devices. This is some of the optical and morphological characterization. You can see as we increase the oxygen plasma exposure, there's a little bit more scattering, and this means that there's more rough, they're slightly rougher, but overall the scattering isn't that, increase in scattering isn't that significant. And you can see from the SEM, the morphology is relatively good. It's relatively smooth surface. You can see though from the real color photographs, there's a darkening of the silver due to the formation of oxides. So we conducted some XPS measurements of the silver after exposure to oxygen plasma for different times. And you can see clearly that there is a shift to lower binding energy as we increase the time. And this is sort of unusual for metals, but it's commonly seen for silver oxides that there's this shift to lower binding energy when you form different types of silver oxides, either Ag plus or Ag2 plus based oxides. And in our case, we were seeing Ag plus. So that would be then the formation of the Ag2O oxide. And also potentially carbonates. So we were seeing by analyzing the ONS and the CONS the presence of silver carbonate as well, forming for 1 second and 4 seconds, but that reduced over time, probably because there's some residual contamination or carbon on the surface during the plasma exposure. And you can see for 7 seconds, we form predominantly silver oxide, Ag2O, even though that's there in actual for all of the cases as well. So we have some silver carbonate and some Ag2O as well forming on our metal electrode. And then we looked at the incorporation of these partially oxidized silver electrodes. So we actually did a previous study where we looked at the thickness of these oxides, and for 1 second, they're less than 5 nanometers in thickness. And you can see from the device behavior that the longer exposure time, sorry, the shorter exposure time, 1 second, produces the lowest turn on voltage and has a high current density, almost as good as that of a silver MOO3 interface. So you can say that the oxide is functioning almost as good as MOO3, but we don't have to do that additional deposition step. And also consistent with those IV curves, we saw that the barrier height was lowest for the 7-second case, as well as the turn on voltage being lower in general for the silver oxides compared to the silver. However, overall, the current density was best for the 1-second case. Again, probably due to lower series resistance compared to the other two. Zhangkai also looked at the stability of these devices, and you can see compared to silver only, which the barrier height changes as a function of time more so than compared to the intentionally oxidized surfaces. So they stay very constant over time. Another student of my group who graduated a number of years ago, Chris Petukov, looked at these oxides. As I mentioned, he looked at the thickness of these oxides as well as their effect on the optical properties of metasurfaces. And they don't really change the optical properties very much when we expose nanostructured silver. These are with 30 nanometer silver particles or 60 nanometer silver particles. You can see that the scattering is slightly increased when we partially oxidize the silver surface. And he did some transient absorption measurements, and he showed that the actual addition of the oxide was very good for photovoltaic, for maintaining a high polaron population in P3HT. You can see here for smaller particles on the silver electrode, when they're oxidized, there's or actually you can see the 30 nanometers, the oxidized compared to the unoxidized case, there's an increase in the polaron population. And to an extent that it's almost as good as that of the 60 nanometer particles, which increase the polaron population by increased light scattering. So addition of the oxide promotes or maintains the large presence of free carriers, positive free carriers in the P3HT, which aids in increasing the photo current. In the second study, I want to talk about our collaboration, as I mentioned, with the Gallipini group in Rutgers Newark. This was led by my graduate student, Sneha, and she collaborated with Marzai Hedari, I'm probably pronouncing it incorrectly, from Elena's research group. So they worked side by side on the development of these SAMs for integration into F8BT-based hole-only devices. And so Sneha has focused primarily on studying the binding and the performance in the devices. And Marzaya developed these, synthesized some new types of SAMs, compounds for use as SAMs, where we were able to get more than one binding site from the molecule. So the idea was to use these lipoic acid-based SAMs where we could actually potentially get better coverage of the silver and may even improve the stability of the silver compared to more traditional SAMs used for organic optoelectronics like 1-decane thiol. So this is just an example I pulled from the literature on the use of SAMs in polymer field effect transistors. The idea has been around for quite a while, but for OFETs, the idea that you would add SAMs to silver back electrode and then spin coat the polymer on top, and that will improve, the SAM will improve the charge injection into the F8BT. And so they looked at a few different self-assembled monolayers, again, with just one sulfur attachment, PFDT and 1-decane thiol. And they showed that depending on the self-assembled monolayer, you can either get an increase in the surface work function or a decrease in the surface work function of the gold in this case when they use those SAMs. And they saw a big improvement in the performance of the field effect transistors in the presence of the self-assembled monolayers. So this was using F8BT as the active layer. So that's why I chose this as a semiconductor. That's why I chose this example, just to show that the idea has been around for a while, but it hasn't been looked at for inverted optoelectronic devices where we're actually, doing light absorption or emission. And ideally as well, it's not in other optoelectronic devices, or sorry, in other OFETs using small molecule based semiconductors, they've looked at silver and copper as well with SAMs on top. But with the polymer-based semiconductors, they primarily use gold instead of silver. So Sneha is the graduate student in my group who began the study and led the study in collaboration with Marzaya Hedari and Elena Gallipini. And you can see these are the self-assembled monolayers we chose for initial study. And the idea is that they would bind to the silver using at these sulfur sites. So we get these two binding sites as opposed to one binding site for decane thiol. And then we used study their performance in these hole-only devices, similar to what Shankar had done previously for the oxides. We confirmed the binding of the self-assembled monolayers to the silver using XPS of the sulfur 2P peak. And you can see compared to the neat compound, the self-assembled monolayers on silver show shifting to lower binding energies of the sulfur 2P peak, which indicates that it has bound to the silver. You can see the surface morphology here, which was measured by my student Hemant Madali, that you can see there's an increase in the surface roughness as well as increase in grain size when we apply the self-assembled monolayers to the bare silver. Overall, there's some consistency between the degree of roughness and coverage of the self-assembled monolayers, although in the lipoic acid case, the lipoic acid case here, we see better coverage compared to the 1-decane thiol and the butyl lipoic acid. So in the devices, we found that the lipoic acid on silver showed the best performance as opposed to these modified compounds. And you can see, for example, the barrier height is reduced compared to bare silver, as well as is lower than the other cases, and also the 1-decane thiol, which is sort of the control self-assembled monolayer. You can also see that the current density has increased very significantly for the lipoic acid compared to the bare silver. The turn-on voltage is also reduced. And then second best is the phenylbutyl lipoic acid compound. You can see that that's also been reduced compared to bare silver and is almost as good as the lipoic acid case. We carried out UPS, ultraviolet photoelectron spectroscopy, to also further confirm whether this is a work function change. This improvement was due to a work function change or a morphology change of the polymer. You can see for the La on silver lipoic acid that there is a lowering of the whole injection barrier. And for the other phenylbutyl lipoic acid case, there is no change in the work function. So we hypothesized the improvement that we saw with this particular compound was due to an interaction, a better interaction with the semiconducting polymer because of the aromatic group at the end of that compound. And so further studies are ongoing in this area to look at the stability of these SAMs on the silver. One of the whole goals of looking at these interfacial layers is to improve the stability and enable air processing of these devices. And so those are ongoing, as well as potential future work on looking at alternative compounds that will create a stronger interaction with the semiconducting polymer. So in the final study, I'm going to talk about our work on two-dimensional materials and their application to plasmonic surfaces to look at how we can improve electron collection from an organic photovoltaic layer. And this work was carried out by my student who's long since graduated, Chris Patukov, in 2016. But it shows the other side and also another type of interfacial layer that shows the N-type behavior on these silver electrodes. So this study was actually conducted on both planar silver and nanostructured silver. And he created these silver nanostructured back electrodes using thermally evaporated silver through a nanoporous alumina on silver. And then we peeled off the anodic alumina and we created these particle-based silver films. And we did a lot of optical characterization using dark field backscattering to show improvements in light absorption and scattering and to detect the plasmonic modes that were created by these plasmonic surfaces. So he did, in collaboration with Keshav Dani's group in Japan, in OIST, where he's now a postdoc. He carried out transient absorption, transient reflectivity measurements of the 2D materials and in the absence, or sorry, the plasmonic metasurfaces in the absence and presence of 2D materials to look at the population of charges in the P3HT PCBM coating. So essentially we're starting with a plasmonic silver nanostructured back electrode, which we call our plasmonic surface. This is the dark field scattering from that surface. You can see the blue scattering, which is characteristic of the silver particles. And this is just the scanning electron microscopy of the bare surface. And then he applied a MOS2 layer by transferring a chemically exfoliated layer onto the plasmonic surface. You can see there's partial coverage. It doesn't fully cover the structures. It's not fully conformal, which is one of the disadvantages of using these types of 2D materials. However, it was quite successful in terms of improving the electronic properties and the absorption in the P3HT. So you can see, for example, in the presence of the MOS2 on the metasurface, we see greater light scattering due to the presence and the interaction of the MOS2 with the metasurface. This is the image of the actual semiconductor on the MOS2 on the metasurface. And you can see without the MOS2, there's not quite as good scattering. So clearly the MOS2 is enhancing the scattering as well. So the pump probe reflection measurements that he carried out were of the polarons and excitons in P3HT in a P3HT PCBM blend. So that's the typical bulk heterojunction photovoltaic layer used for prototypical photovoltaic devices, conjugated polymer-based photovoltaic devices. They were excited at 400 nanometers, and then to probe the polaron and exciton population together, the probe wavelength was set at 1000 nanometers, and then to probe just the exciton population only, he probed at 1050 nanometers. And you can see the polaron and exciton population is relatively modest, I would say, for the P3HT on planar silver, and comparing the exciton intensity with the polaron, or sorry, delta or all over OR value, you can see that they're relatively similar. So the majority of the silver is expected to be from the excitons, although the increase at longer time is from the polarons. You can see when you add the metasurface, there's a strong increase in both the polaron and exciton population, but more so in the polaron population. As you can see from this larger increase here, we're probing both polarons and excitons, but the smaller increase for just the excitons. And oops, let's see, let me see if actually, yeah. Okay, so for the addition of the MOS2 on planar silver, there's actually an improvement as well on the polaron population, and that's without the metasurface. And then combining the two, we get a very significant improvement in the polaron population by more than a factor of 6 in the presence of the MOS2 on the metasurface. So what's going on here essentially is that when the excitons are formed in the P3HT and as well in the MOS2, when they absorb that 400 nanometer light, then there are excitons formed, and then there's efficient charge transfer from electron transfer from the P3HT and from the PCBM to the MOS2, which is then collected at the silver metasurface. So that, in other words, there's efficient electron transfer to the metasurface via the MOS2, and the holes in the MOS2, as well as any polarons in the P3HT, remain in the P3HT because we've no counter electrode in this measurement. And so the polaron population has increased. This would mean that there would be a greater photocurrent in an actual device because we collect more polarons at the anode. So this is showing, proving then that we can improve this interface between the metasurface, the silver metasurface, and the semiconductor and polymer using this MOS2 interfacial layer for improving electron transfer. So I'm leaving it there, and I'm happy to answer any questions. I'd like to thank the PhD students in my group that carried out a lot of this work: Shankar Cheng, Sneha Srikumar, Hemant Medali, and Christopher Petukov. And also I'd like to thank our collaborators, Mirzaia Haidari, Elena Galapini, Keshav Dani, Sylvia Rangan, and John Vurek, who helped with the measurements we did XPS and UPS at LSM. So thank you. I'll take any questions.
I have a question.
Okay, go ahead.
Around about slide 23, when you're